Okay, so today we're going to talk about one of my favorite neural networks, and that is the convolutional neural network. And they are typically used, or I should say primarily used for image recognition. And the reason they get their name is because what we're going to do is we're going to convolve a mask with some image. And if we do that, we'll get a set of values that we can then use to determine features of the image that we're convolving. So we're going to convolve these two and get some values for our neural network so it can use that for feature detection. So we're going to start off with a very simple example where I am going to build a grid of values, random values. So here we go. Bear with me if my table is not quite the nicest that you've ever seen. So here we go. And there we go. Now I'm going to grid this into a 6x6. So, oh, this is actually turning out better than I thought I could do. So my grid is almost done, and then I get to fill it full of all sorts of numerical values. Okay. Oh, I know I'm going to mess up somewhere. That's okay. So let me fill this in with some values. We have 2, 4, 7, 0, 1, 3, 1, 3, 8, 9, 4, 2, 5, 7, 6, 0, 3, 6. We're halfway done. 8, 5, 9, 0, 1, 2, and 3, 4, 7, 1, 5, 4. And 9, 8, 1. Ooh, 4, 6, 7. Okay, that was a lot of work. So I have here a 6x6 grid, and what these values are going to correspond to, at least this is the abstraction we're going to use, is that they are corresponding to pixel intensities in a 6x6 pixel image. So we'll say that 9 is where it is all on, so a white, and 0 is a black pixel. Alrighty, so now we are going to convolve this with a filter, and sometimes I'll say filter, sometimes I'll say mask. It's the exact same thing. So it's going to be a 3x3 filter, and this filter is going to have some very special values in it. It's going to have 1, 1, 1. Oh, let me try to write a 1 again. So 1, 1, 1, 0, 0, 0, -1, -1, and -1. Okay, so the way I'm going to convolve this 3x3 filter is with my original image, the 6x6 image, is I'm going to overlay this filter on top of a grid of numbers over here in my image, and I'm going to multiply the values in my filter with the overlaid value in the corresponding pixel, and then I'm just going to add them all together. So this is going to give me a resulting matrix of, let's see, it's going to be a 4x4. I think I can fit it all on here. Here we go. All right. So we're going to start off. Let me change my pen color where you can track this a little bit better. I will start off by overlaying the 3x3 filter over this set of values right here, this 3 by 3 set of values. Okay, and so I'm going to get a value that I'm going to put into this very first box up here. How do I get that value? Well, that value is going to be 2 times 1 plus 0 times 4. Oops, let me keep that the order, the same order so that I don't wind up, it doesn't wind up being difficult to follow. So 2 times 1 plus 4 times 0 plus 7 times negative 1 plus, now we move down to the next row, 1 times 1 plus, that's a time symbol, I promise, 3 times 0 plus 8 times negative 1, I'll just do it like that, plus, last row now, 5 times 1, so 5 times 1 plus 7 times 0, 7 times, I'm running out of space, and then plus 6 times negative 1. Oh, I don't think I can squeeze it in there. Let's see, 6, if y'all can get by with it. That sort of looks like 6 times negative 1. All right, so this is going to give me 2 plus 0 plus negative 7. So that's a negative 5. Plus 1 is negative 4. Plus 0, still negative 4. Minus 8, negative 12. Plus 5, negative 7. Plus 0, still negative 7. Plus negative 6, which is going to give me a final value for this box right here of negative 13. Okay? Now, for my next one, I'm going to change my pen color again. And let's go with this color. I'm going to move my filter one set of pixels to the right. So now my 3 by 3 is going to be this grouping right here. And I did the exact same thing I did before. This time I'll start down here where I'll have a little bit more room when I'm actually drawing this. So let's see, if I start here, I'm going to get 4 times this 1. So 4 times 1 plus 7 times 0, 7 times 0 plus 0 times negative 1 plus 3 times 1. I guess I can do it like that. Plus 8 times 0. God, it's hard to do. Plus 9 times negative 1. And then plus 7 times 1. Plus 6 times 0. And then plus 0 times negative 1. Okay? So I'm going to wind up with 4 plus 0 plus 0 plus 3, 7 plus 0 plus negative 9, negative 2 plus 7, positive 5 plus 0 plus 0. So I put a positive 5 up here. I'm going to do one more just to make sure it's very, very clear what's going on. Change pen color. Now I'm going to be looking at this group of 3 by 3 pixels. I'm going to convolve my very special filter with that. So here we go. I'm going to get 7 times 1 plus 0 times 0 plus 1 times negative 1 plus, now we'll move to the next row, 8 times 1 plus 9 times 0 plus 4 times negative 1. Last one, 6 times 1 plus 0 times 0, and then finally plus 3 times negative 1. Okay, so I'm going to get a value of 7 plus 0 minus 1, so 6 plus 8, 14, plus 0, minus 4 is 10, plus 6 is 16, minus 3 is 13. So I'm going to put a 13 up here. Okay. So as I move my 3x3 filter across my pixelated image here, I'm going to be convolving the filter with the underlying pixel values, and the total result I'm going to be storing in a new matrix that I have up here. In this case, it's a 4x4. How did I know it was a 4x4? Well, if I change my pen color again, you can see that if I move over one more set, I reach the end. So that would happen with a value in here. And then if I move, once I reach the very edge, now I take and shift, go all the way back to the beginning and shift down one. So the next one would look like, let's see if I can get this one to work. This set right here would be the next 3x3, and whose convolved value would be stored in this box right here of my new matrix. Okay, so those are the basics of how a filter is used and convolved with an underlying pixelated image, and you get a set of values. Next, we're going to look at what those values mean and how we can actually pull features out from all of that. So let me clear the area and let's start again. Okay, so like magic, a new set of pixel values have appeared in our 6x6 grid, and we are again going to convolve this with a 3x3 filter, and that filter is going to look like exactly what we had before, with those special values of the rows corresponding to values of rows, the columns 1, 1, 1, 0, 0, 0, and -1, -1, -1. Okay? Now, if I convolve this again with the pixel over here, the pixelated image, I can get this 3x3 right here. I'll start off with that. And so I'm going to wind up with 4x4 with the following values. I won't go quite into as much depth here because it's not too hard to see since all the values are either 9s or 0s. So here we go. That is going to give me a value of 9 times 1 plus 9 times 0 plus 9 times -1. 0. And same thing for the next row and the next row. So I will wind up with a 0 here. Okay? Now I'm going to shift over 1, and let me change this to maybe orange. So this group right here now, and I'm going to get something very interesting, because I'm going to get, if you'll allow me to do it this way, there are 1s in this column, 9s in the column that corresponds to, that's convolved with. So that's going to be 9 plus 9 plus 9, which is 27. Then I'm going to have 0s, because 0 times all of these 9s is just a 0 for that column. And in this column, I've got 0s here and -1s here. So again, it's going to be 0s for these two columns. So the grand total is going to be 27. Okay, and I'm going to shift over again, and let's go with that color right here. Okay, and so I'm going to again get 1s times 9, which is going to be 27, and then 0s in the other column, so that corresponds to 27. And then if I shift over one more time, I'm going to get this set. And this set, you can already see what values I'm going to get there because it's 0s everywhere. So no matter what's in my filter, I'm just going to wind up with a 0 over here. Okay? That's going to hold since every one of these mask that I can draw is going to have the same pattern as I move across my pixels and convolve the filter with them. So it doesn't matter if I shift it down to this one right here. I'm still going to get the same value that I had with the blue, the light blue value. So let me go back to my original yellow and fill in the rest. So I'm going to get 0, 27, 27, 0, 0, 27, 27, 0, 0, 27, 27, 0. Okay? Now, what has just happened? I'm getting, with my resulting matrix, I'm getting zeros on the edges here, and I'm getting 27s in the middle. And that has meaning. This is how it's going to pick out features, because this box right here has a very special name. This is an edge filter, and what it does is it detects when there is a vertical edge, a vertical transition from one high intensity to another large intensity. In other words, from white to black. If I transition from white to black in the middle of my image, over here in my resulting matrix, I'm going to have positive 27s where that transition is occurring, which is in the middle. Okay, so what I've done is, by convolving this edge filter and moving it across the image, when I have large positive values like this, I have an edge where that basically occurs, and if it's the middle of this resulting, the edge was somewhere in the middle of the image. Okay, so I'm going to change things around just a little bit. So let me clear the board again. Okay, so again, magically a new grid has appeared, and this time the pixels, instead of going from 9s to 0s, this one is transitioning from 0s to 9s. So black pixels to white pixels, and I'm going to convolve it with the same edge filter. Edge, I can spell filter, there we go. And so that is going to give me, again, a 4x4. Fill that in, but now I'm going to get different values. So here we go. Worst 4x4 grid ever. All right. So when I first move it across, I'm going to convolve the filter with this initial set right here, and I'm going to wind up with a 0. And then here's where it gets interesting. When I move over to this group, I'm going to get something different. I'm going to get zeros when it multiplies by the 1 column, zeros when I multiply by the zeros column, but now I'm going to get 9 times -1 plus 9 times -1 plus 9 times -1. I'm going to get a negative 27 in my 4x4. Okay, and if I continue to fill this out, I'm going to wind up with negative 27, 0, 0, negative 27, negative 27, 0, 0, negative 27, negative 27, 0, 0, negative 27, negative 27, 0. That's a 7. Alrighty, so what changed? Well, initially in the time before, I had my 6x6, and I had all the values on this side were 9s, and on this side were 0s. So I was basically transitioning from white pixels to black pixels, and my matrix was again a 4x4, but it was zeros, positive 27 zeros all the way down. Now, as I'm transitioning from black pixels to white pixels, I'm getting negative 27 in the center column. So what that means is when I transition from white to black with my vertical edge filter, I get large positive values wherever that edge is. And when I transition from black to white with the same edge filter, I get negative large values wherever that edge is. So a single edge filter, this column of ones, zeros, and negative ones, can actually tell where a vertical feature is, and it tells whether it was a transition from light to dark or dark to light. All of that with a single filter. And so this is some of the power of the convolutional neural network. You can get a whole lot of information by convolving the original pixel image with these filters. You get a lot more information than it would initially look like. If you had told me that you could use the same edge filter and you would get information whether you're transitioning from light to dark or dark to light, I wouldn't have thought that was possible, but this is exactly how it works. And to kind of reiterate this, to show how you can get other information from this, if I clear the board, let's see here. And now, instead of using a vertical edge filter, what would happen if I had my large 6x6 and I convolved it with an edge filter that looked like this? I can draw the lines in. I'm going to have 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. This is another edge filter, but instead of detecting vertical edges, this is a horizontal edge filter. And I will get the same type of values, but instead of having a column of values that are either very positive or very negative, where the edges are, I'm going to get values in the interior along the horizontal axis. So it'll be zeros everywhere else and positive 27s, etc., etc. So by using a different filter, in this case a horizontal edge filter, I can now tell where I have horizontal edges in my original image and whether or not it is transitioning from light to dark or dark to light in my original image. So with just these very small changes, we can now actually tell what type of features, the very large gross features of the image are with a single filter. We can get all the vertical ones with one filter and then put another filter in to get all the horizontal transitions. And you can imagine there are all sorts of filters. You can get very complicated and use things that aren't just 3x3s. If I wanted to do some sort of diagonal filter, well, I would change this to be something like, let's see, there we go, maybe 3, 1, 1, 0, 0, 0, negative 1, negative 1, negative 3. Now I have a diagonal filter to detect all the diagonal features inside my pixel image. So these are just a few of the basic ones. There are many types of filters that you can use, but this is how a convolutional neural network extracts the feature information from the pixel image. They do it by convolving filters and performing a mathematical operation on the filter combined with the image and getting a result that it can then interpret and use to tell what's actually in the image so that it can recognize them. Cats versus birds, triangles versus circles, etc. So this is exactly how convolutional neural networks work. And the only thing left to talk about for them before we adjourn is some of the, uh, uh, I guess, definitions and language that are used when you're defining a convolutional neural network, because there are several options that you can set when you're defining these systems. So that will be the last thing that we talk about. So let me clear the board and we will get started on that. Okay, so here we are. We have a new image, or a 6 by 6 pixel image. We have a 3 by 3 filter, and that will result in a 4 by 4 matrix. Now, there is a problem if I am convolving this filter with my original image, and that problem is when I'm convolving this filter with the image, the corners up here, 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 and here only get sampled a single time. So this corner will be sampled when it's this set of pixels. This one up here will be sampled the one time that I have the filter over that set of pixels, and so forth. Meanwhile, the pixels that are in the center of my image are getting sampled over and over and over. So what this can do is this can lead to a disproportionate weight for the center pixels compared to the edges and corner pixels. The way that you can get around that is by introducing something called padding. Padding. And padding simply means that you add rows and columns to, oh boy, I am such an artist, your existing matrix. Okay, so you add, if I add one row and column to the left, right, and top and bottom of my original and fill that in with zeros so I don't skew any of the values, or neutral values, you can think of it as that. But if I put zeros in here, which is typically what is the matrix is padded with, what will happen now is that these corner pixels that used to only get sampled once are going to get sampled several times. So now those corner pixels are actually being represented more over here. The second thing that does, and by the way, this is padding equals 1, because there's a single row being added to top and bottom and a single column to left and right. The other thing that it does is that it expands the resulting matrix. So what was a 4 by 4 turns out, when this is all said and done, I'm just going to do it this way so it's easier to draw, it is now going to be, I can get this up here, there we go, a 6 by 6. So I started off with a 6 by 6 original image. I convolved it with a 3 by 3 filter, and by adding padding 1 to the original image, my resulting image is also 6. My resulting matrix is also 6 by 6. So it allows you to preserve your original dimension of your image, which, again, that can be a nice thing. That way I can get more rich detail about the features that are inside the original image, especially for the edges and corners of the original image. So that's what padding is for, is to add that layer, that row and column to the top and bottom, left and right, so that you can increase the number of times that the sides and corners are sampled to enhance the weight that those pixels have in your resulting matrix, and also preserves the original dimensions. So one of the things, there are two more types of, two more definitions, I should say, for our convolutional neural networks. And the first one is, let's say that I have a grid And I'll do, oh, let's see, something like a 7 by 7. Yeah, I probably should have paused this and so that you didn't have to suffer watching me draw this. All right, 1, 2, 3, 4, 5, 6, 7. Wow. 1, 2, 3, 4, 5, 6, 7. So here we go. We have a 7 by 7. And now we're going to look at the parameter stride. Okay. The stride tells you how many pixels you jump, you leap by every time you do a convolution. So if I have a 3 by 3 filter and a 7 by 7 original image, if I have a stride of 2, the normal stride that is by default is called a stride 1, but if I set my stride to 2, what I'm going to wind up doing is if I start with this set of pixels right here, my next set of pixels is going to be right here. I am leaping over one set. So if I look at the corners, I'd have this corner right here, and that's my upper left. It's jumping over one pixel length to get to the next one. And then I would follow suit and jump over again and have the next one. Let's try a different color. Would be right here. Oh, and I forgot to do the little X right here. And that's the upper left. So you can see a stride 2 is leaping and skipping over pixels. And if I do that, I don't wind up, in this case, with what you might expect. I wind up with a 3 by 3 for my final matrix, which sometimes that's perfectly fine. Striding, you don't lose as much information as you might think. And I should also say that when you are striding and you reach the end, you then hop down 2 pixels instead of 1. So the very next one for this would be right here is where it would start, because I'm going to skip from here down to here and jump over this one. Okay? So stride is basically used to reduce the dimensionality of your original image. You lose some information by doing it that way, but it really isn't as much as you might think. Convolutional neural networks are extremely robust at altering the original image. So that is one of the 2 definitions, which is stride. And now for the very last one, and this is one of my favorites, and we're going to talk about what's called pooling. So pooling. Okay, so let's say that I have a 4 by 4. I can draw that pretty quickly. Okay, so there's my 4 by 4. I'm going to put some values in here. 7, 1, 1, 0, 2, 3, 4, 9, 2, 5, 1, 3, and maybe 6, 3, 4, 1. Okay. Now, pooling is where you take your filter, and in this case, I'm going to use a 2 by 2 filter, and you convolve it with your original image, and depending on what type of pooling, you're going to get a certain result. So let me go ahead and draw the 2 by 2 result before I start my grid rather. Before I start talking about what it is. So there are two types of pooling. And one type of pooling is called max pooling. Okay, and this is by far the most common. Max pooling, you convolve the 2 by 2 with your original pixel image, and you take the maximum value that's within that grouping, and that's what you store in the resultant matrix. And so if I did that again, I'm going to wind up with, for this, I do kind of a stride of 2 to get over to the next grouping, and then I would have, that one would be a 9. That's the largest value in this grouping. And then for this grouping of 4, I've got a max value of 6, and this one I've got a max value of 4. So that is max pooling. The other type of pooling is called average pooling, which is nowhere near as common. And as you can probably guess, average pooling averages the 4 values. So in average pooling, let me do like that. I've got my 2 by 2 resultant matrix is going to have values of, well, the average of these values is 3.25, 3.25. Average of these 4 is 3.5. These 4 is going to be 4. And finally, these values right here is going to be 2.25. So average pooling averages those values. Max pooling takes the maximum value of those groupings. Initially, you might think that if I am trying to preserve information about my image, average pooling would do a better job because it gives me kind of a blend of all the surrounding pixels. But actually, the one that preserves the most information about your original image is max pooling. Max pooling is used to reduce the dimensionality of the original image. And if you look at this where I have a 2 by 2 and I end up with a 2 by 2, I'm basically halving. If I have a 2 by 2 filter, I am halving the dimensions of my original image. So if I started out with a 300 by 300, I do max pooling with a 2 by 2, I'm going to wind up with a 150 by 150 matrix. And by preserving the largest pixel value in each group, I actually maintain most of the information that I would need to extract further features. So max pooling is what preserves the actual information. Average pooling just kind of smears everything together. It's a blending effect. So if I'm picking out sharp features, very distinct features, I'm typically going to do max pooling. To be honest, I can't think of a good reason why I would want to do average pooling for standard networks, standard images. But you will see max pooling used all the time. It halves the dimensionality in each direction, so you get a reduction of a 4-fold reduction in the matrix size, while still preserving most of the information. And so with that, that is everything you need to know about convolutional neural networks so that you can actually set all the parameters up yourself to run them on different images to be able to classify them. That's pretty much it. So be fearless, and I will see you. Well, probably this might be the last one. So I'll sign off by saying I definitely enjoyed making all these videos. So I hope you've enjoyed watching them. Take care. Bye-bye.